the remainder of this chapter. And this is what we started talking about last time, the issue of the utilizability. And this is a concept actually that we are going to introduce briefly today, but we are going to talk about that a lot when we come to the applications. And by the applications, I basically mean when we are talking about the solar collectors in general. When we are using a solar collector, basically it is receiving solar energy from the sun and it gets heated. So its temperature increases. Because the temperature increases, it becomes greater than the ambient temperature around it. So it will start to lose energy to the surroundings, mainly by convection. There could be an onset or a condition where the energy received from the sun, either that can be in the early morning or late in the afternoon, where the energy which is received from the sun is low and it is equal to the amount of energy which is being lost to the surroundings due to the increased temperature. This value is what we refer to as the critical radiation level. So when we are considering the energy balance, again, there is useful energy in, we call it gain. And the losses due to the temperature of the collector being higher than the atmospheric or the surrounding temperatures. If these values are the same, the gain is equal to the losses, then we call it a critical radiation level. For the solar collector to work, the value of the gain should be greater than this critical radiation level so that it has a higher temperature that is not where the heat is not all lost to the surrounding in the form of losses, but there is additional gain, there's additional input that can be used for heating water or heating the air, depending on which fluid that you are interested to heat. If they are the same, then the collector is useless. It is receiving energy and losing the same energy, which does not make sense for our operation. You need it, or you are using a solar collector because you need to heat something. And if this value is negative, then you better not use the collector if this is the case. And that normally would happen maybe sometime after the sunset, where the unit is hot and there's no sun anymore to heat it. So it's just losing energy to the surrounding. And that's why they try to make as much as they can the issue of energy storage, so that if you are heating water, then this water is going to be stored in a very well insulated tank. If you are heating air, air is going to be stored in a very well insulated system so that it keeps its temperature higher for several hours after the sunset. So we're talking about the issues where we are doing this kind of comparison, the IT, which is the gained energy falling on the collector minus the critical value. And the critical value again means it is the value where the heat gain from the solar energy is basically equal. Sorry, there's something which is happening here. Is equal to the losses, and that is something that we try to avoid. Yeah. And they are given here some sort of a way that we can measure this fraction of total energy which is falling. I here, or IT, is the gain, energy gain, which is coming from the sun. ITC, the C stands for critical. So this difference divided by over T gives some sort of a ratio that represents the utilizability, and this value goes from 0 to 1. 0, it means that the values are equal. Greater than that, greater than 0, it means that we are making use of the energy which is falling from the sun, depending on how much are the losses compared to the heat gain. The bigger the difference between them, the bigger the heat gain compared to the losses, the better the utilizability. You are able to utilize your solar collector in a better way. And to look at this again, it can be represented not only by the figure, but it can be represented graphically. If the total solar energy which is falling is given by this figure that you can see here, it may start at 0 at the start of the sunrise, and it will start increasing until it reaches a maximum value at noon, and then it will start decrease so that it reaches 0 again at night. So if this value is the critical value, then whatever is above the critical value is the useful kind of energy that we are getting, or the gain. The ratio that is phi that we are taking here for a certain hour would be the shaded area, which is basically a ratio of this shaded area divided by the total amount of radiation which is falling over this hour. You might be interested to gather information like, for example, what is going to be the utilizability of the hour between 10 and 11 o'clock in the morning during the whole month of February, which means that you are going to look at the whole month of February, maybe record the values that you are getting, calculate the temperatures, see how much solar energy is falling into the collector, measure the surface temperature of the solar collector. This is where it starts to lose energy by convection to the surroundings, and measure the air temperature around it so that you can see how much is being lost and how much is being utilized actually for heating. And then you can average it and see, for example, from 10 to 11 over the month of February or March or whatever, this is the value of the utilizability there. And then a month average can be estimated. This can be during 1 hour of the hours that we are using here. This value is not going to be a constant value. I mean, it's just some sort of a trend. The more you can get this value, the more beneficial it is. What I mean by that is that if we are going to do it over the month of February of 2021, and being able to measure what's the value of the utilizability factor, which is phi, over this month, it gives an indication. But it would be more useful if we have this value and the value of the same hour, 10 to 11, of February 2020 and 2019 and 2018. This will give us an indication that for this place, which is, for example, Dahran, during the month of February, over 10 or 20 years, the average utilizability is equal to this quantity. Why does it have to be over a long period of time? Because the weathers from year to year or from day to day may change. You may have days with dense clouds or less clouds. So the values are going to, the amount of energy gain, the wind speed that may increase the convection coefficient, and the losses are going to be higher, may vary from hour to hour or from day to day. This is why having a long history of these values over a large number of years would make our calculations more effective, more meaningful, and meanwhile it will help us predict if I need to use a solar collector for the next 20 years. Then I would know that this is the kind of useful gain that we are going to get at this hour, and then the next hour, and the next hour. So I can just make my system in a way that would satisfy a certain load. Suppose that I need to use solar collectors in order to heat water for a house. How many solar collectors should I need? I know that our utilization in the house, for example, are going to be, say, 100 liters per day. To heat the 100 liters per day from the ambient temperature, which a record should be there for an average ambient temperature, to a value of 40 or 50 degrees centigrade, for example, 55. It depends on what is your design temperature. Then how many solar collectors do I need? So to have my calculations to be more reliable, I should have reliable data that is representative of the weather conditions over this part of the year. And definitely that can be done, but normally for this case, we do of like average over a whole year, not only a month, but it's a way of looking at the data and how you can make use of the data to estimate the size of a certain heating system that you may need. I'm not talking about the generalized utilizability now, but we're going to talk about it in details and part of it in chapter 4, and the rest is going to be in the applications that we're going to have. So in this chapter, basically, we've been looking, or we started looking at what are the instruments that are used to measure the solar radiation. We talked about the pyrheliometers and the pyranometers. Pyrheliometers are used for measuring the beam radiation. Pyranometers are being used to measure the total radiation. And some sort of pyranometers with a shaded band are being used for measuring of the diffuse radiation. And you can verify that by the summation of the beam and the diffuse radiation is resulting in the total radiation. Radiation data are available in several forms. Some of them are available on a daily basis, some are available on hourly basis, and some are available, or mostly are available in horizontal surfaces where you can adjust it. And we have seen how to adjust if we start with radiation on a horizontal surface, how we can extract or get the corresponding value of radiation incident on a sloped surface at a certain angle. So they are available on hourly basis for a limited number of stations and on daily basis for many stations. And we have seen cases also in the chapter where we can make use the radiation of the daily base so that we can extract how much would be the radiation on our hourly base, taking our reference at the solar noon and then moving plus or minus number of hours around it so that it covers the whole day. We have different forms accordingly for solar radiation, and being able to change it from one form to the other is something that we have been discussing here in this chapter. The daily average values, the monthly average values are useful amounts of data that we need, and we are going to make use of these. This is why we are looking at getting the picture as complete as possible so that we can estimate, for example, how much is the total radiation at any location at any time through the whole Earth. And this is important because we are doing that so that we can be able to accurately estimate how much the size of a solar field that you need to design so that it fits a certain load that you need. We cannot predict solar radiation in future, but if we have a good record of the history of the solar radiation for a certain location, then we can approximately get some sort of a prediction to how we expect solar radiation to be. And the more data that we have in terms of values all over the years, the more accurate our prediction for the radiation to occur in the next year or so. We talked about the estimation of beam and diffuse radiation, and we looked at different models of the diffuse radiation as well, so that we can calculate it based on isotropic model or anisotropic model, and we have taken a couple of correlations for the anisotropic models that can be considered for our calculations or our estimate of the total amount of radiation which is falling into a surface that include the beam radiation, the diffuse radiation, and the reflected radiation from the ground. And finally, we talked about the concept of the utilizability and making sure that the solar collector that you have after the losses to the surroundings is still able to do the work of heating a certain fluid that is passing through. So that was basically what we have covered in this chapter. You are going to find that there is a set of homework, which is homework number 2. It's a 4 problem. This is available now on Blackboard, and the due date is a week from today. They are just 4 problems. They will not take much time, but they will just cover some of the main elements that we have considered in this chapter. Next is again to remind you that in this part of the course, what we are doing, We are just laying sort of a foundation to the main issue or the target of the course, which is basically considering or talking about solar collectors. So we talked about radiation, the definitions, the angles, how to calculate the value of radiation falling on whatever the slope of the surface at whatever location, whether it is daily or yearly. Now let's have a look at some background information that you have covered before, but we are going to go through some sort of a reminder of these topics, which are basically the principles of heat transfer. So we're going to go through sort of a revision or a quick reminder of selected heat transfer topics that are relevant to what we are doing in this course. No, this is not what I wanted. I wanted to share the big screen, which is this. I'm just something here I'm noticing is that I can see that the participants are 20. You are supposed to be 19. So is there anyone who's logging in twice from his computer as well as his mobile, for example, or we have some additional persons here? That's interesting. I'm going anyway to check that after our class, just to look at the names and being able to see. So what we're going through today, or what we're starting to look at, some selected heat transfer topics. And by selecting heat transfer topics, we are basically going to talk about a couple of modes of heat transfer. One of them is radiation. Radiation has been given briefly only in the heat transfer course. The heat transfer course, if you remember, is a heavy course where you basically covered conduction heat transfer and then convection heat transfer. And then when it comes toward the end of the semester, you have maximum of 6 classes to talk about radiation. Sometimes if we used to be, if we are a little bit late in the course and we could not, and it took us like more time than expected in covering conduction or convection or both, then we reduce the number of classes given for radiation from 6 to 5, sometimes to 4. It depends on the changes from one semester to another. So the point here is that sometimes your coverage of radiation in heat transfer course is brief, and sometimes you get a feeling from the numbers that you are dealing with in problems, especially in problems that have multi-mode heat transfer. You may have a problem where you have a combination of conduction, convection, and radiation, and some sort of a feeling that we may get that unless there is combustion or fire, or basically very high temperature source, then radiation can be neglected, which is some sort of an unrealistic estimation of the value of the radiation because it's a relative thing. We'll be talking about that during this chapter several times, and probably I can just mention some of the work that we have done that would show that no, this is not the case. But there are some cases where radiation, even at a low temperature, can play a substantial role in the total heat transfer from one surface to the other, or from one open surface to the surroundings. So we are intending to review some aspects of heat transfer that are relevant to the design and analysis of solar collectors and systems. And then I'm putting this as a reminder so that you just keep it in your mind that what we are doing so far is some sort of laying foundation to talk about the solar collectors, their design and their analysis. We'll start by reviewing radiation heat transfer that is usually overlooked in heat transfer courses. Next sections would preview or get into convection heat transfer. Convection is extremely important in engineering applications. Let me tell you, for example, that solar collectors are gaining heat by radiation from the sun, but heat is transferred to the fluids mainly by convection. So convection is one of the most important modes of heat transfer when it comes to industrial applications or even domestic ones. So we'll be looking at internal flows, because solar collectors may have flow inside a pipe. So understanding the heating mode of the fluid here is important. So the issue of internal flows and being able to estimate the heat transfer coefficient based on the conditions. To remind you, in heat transfer, you had something first to define whether the flow is laminar or turbulent, whether it is developing or fully developed, hydrodynamically or thermally, and they're used to have some correlations for the criteria to determine whether it is developing or a fully developed flow. In the industry, we prefer turbulent flow, because turbulent flow is characterized by high heat transfer coefficient. And normally this is what you need. You need to transfer as much as possible of heat to the fluid. And that's why we like turbulent flow. It is a little bit more complicated in the theory, but in terms of practical applications, that's something that we always look for. To the extent that sometimes in heat transfer problems, if the flow is laminar, we put something called turbulators. We put it inside the channels, inside the pipes, which are basically something that can trigger turbulent flow. You can create some sort of randomness, and then the fluid becomes turbulent accordingly, even at a Reynolds number which is probably below than the critical value between laminar to turbulent. Why is that? Because again, high heat transfer coefficient is something that we need. Even to the design of the flow flow around or across tubes can be done in a way that you try to generate as much as turbulent flow as possible. You probably, if you cover the topic of a flow across tube banks in heat transfer course, so probably we can see that the value of the Reynolds number, critical Reynolds number, is a value which is basically quite less than 2000. Anyway, the radiation heat transfer has a major role to bring the energy to the earth. And you normally use some sort of a collector with a receiver. The receiver is basically a black body, so that you can receive as much radiation as possible, so that that surface absorbs the radiation, gets heated. And then this heated is conducted to the tubes and then convected to the fluid, and the fluid gets heating accordingly. In engineering practices, in many cases, we neglect the effect of radiation, which may or may not be true based on the application that we have. Are we talking about sort of a flow with convection? Is it laminar or turbulent? I mean, is it free convection or forced convection? In forced convection applications, it may make sense that you neglect the effect of radiation unless the temperature is too high, because convection is going to be dominating. But in problems like convection heat transfer with natural convection, for example, natural convection inside an enclosure, where a temperature difference of 10 or 15 degrees centigrade. And normally for these temperature differences, the first thing that comes to our mind that, okay, let's neglect radiation because the temperature difference is small. But for these cases where the temperature difference is small, if we have natural convection, then you cannot neglect radiation, because it becomes almost the same order of magnitude of convection. And probably while we are going through the slides of this chapter, I'll give you some examples from our own work that we have done. And we showed that there are some cases that you cannot overlook. You cannot say that radiation is negligible there. So it's a matter of a relative thing based on basically how much is the coefficient of heat transfer that you may have. Thermal radiation is electromagnetic energy which is propagating through space at the speed of light. When it comes to solar energy, we are interested into the thermal radiation, especially if you are looking for heating. If you are looking for generating electricity, you might be interested in the beam radiation and the light in general. Radiation are emitted only due to temperature. I probably mentioned it in some of our classes earlier that any surface greater than, at a temperature greater than 0 Kelvin, it starts to emit radiation. Are we interested in the absolute value of radiation? No. We are normally looking at what is the net radiation between two surfaces or a surface and its surroundings. Then for this case, that's what we're interested in, because the net heat transfer is what we want. I have a temperature, a certain body at a temperature of 60 degrees centigrade, another one is at 20 degrees centigrade. The first one emits radiation that falls into the other. The second one emits radiation that falls into the first. What is it that we are interested in as engineers? It's the net amount of radiation, because at the end, one of them is transferring heat to the other one, and heat transfers from the higher temperature to the lower temperature surface. The net amount is what we are interested in. So radiation, yes, it is emitted by the virtue of temperature. Temperature is the only reason for transfer of heat by radiation. These emissions that are resulting from higher temperature surface, temperature, as you may know from the thermodynamics, it's an indicator to the level of internal energy. I used to say that example when I was teaching thermodynamics, that in your car, whenever you are driving, how would you know that you have full gas, your full tank, or the tank is going to be emptied? By looking at the dial that you have in your dashboard that have F, which means full, and C and E means empty, and in between. So this dial is an indication of the level of gasoline that you have in your tank. The relation between temperature and internal energy is similar. Temperature is an indication of the internal energy. Higher the temperature, the higher the internal energy. The lower the temperature, the lower the internal energy. This is in one hand. On the other hand, what is internal energy? Internal energy is a combination of different energies that are on the molecular level. Kinetic energy of the molecules, spinning energy, translational energy, vibrational energy, all of these are quantities of energies that are added up together to represent what we call internal energy. So higher temperature, higher internal energy. Higher internal energy, it means that the molecules are going to be excited and they are not going to reach to their original case until they emit part of the energy that they have, and they emit it in the form of electromagnetic waves so that they can retain their positions again in the atoms. And that, as you can see here, it is occurring over a wide range of wavelengths. For each wavelength, there is a certain amount of emitted radiation which is associated with that. The electromagnetic spectrum is defined by the wavelength and the frequency. Here you can see that a certain range of wavelength that starts from gamma rays and cosmic rays in one end, the end of short wavelength, to the other end of long wavelength, where we have the radar, the TV, radio, short wave and long wave radiation. This is all a representation of radiation. This is all characterized by the wavelength, but it is not all thermal. Gamma rays are not generating any heat. Radio and TV rays are not generating any heat. But heat is generated for the thermal radiation range that you see here, which is starting from roughly 0.1 up to, we used to say 100, but here it is extending over 100 to maybe 1,000. So going from a very small quantity or very small amount of the wavelength, short wavelength, which is bringing us in the ultraviolet region, to the long wavelength, which is taking us to the infrared region. This is where the electromagnetic waves are resulting in temperature change associated with thermal radiation. These values or these vertical lines that we have here are not distinct. For example, can we say that gamma rays would stop at 10 to the power of minus 4 sharply, so that if you have something which is little higher than 10 to the power minus 4, gamma rays will not be there? Shall thermal radiation be exactly from this value to that value? No, I mean, this is some sort of borders that are not really sharp. So the limits here are not sharply defined. It may more or less represent some sort of a range of some sort of flexible borders. Then when we are looking at the solar energy, it is occupying here this pink square. It is occupying a fraction of the thermal energy, thermal radiation. Part of it lies in the ultraviolet, as you can see here, and then it is covering the whole visible range, which is basically between wavelengths of 0.38 to 0.78, and then part of the infrared as well. So that's thermal radiation, or this is the role of radiation associated with the sun. It is within this range of the wavelength. Coming to the relation between the speed of light and the medium. The speed of light in a medium is equal to the speed of light in vacuum, which is almost 3 into 10 to the power of 8 meters per second, divided by n, which is the refraction index. It depends on the medium through which it is flying. And this is why there is the arrays that are reaching in water are broken, for example, due to the refraction index. Lambda is the wavelength, and nu is frequency. As you can see here, or as we will see later in the representation of thermal radiation, there is a direct relation between the amount of radiation, the energy level, and both lambda and the frequency. And you can see here, if we're talking about a certain medium, say we're talking about speed of electromagnetic waves in vacuum, then the speed of light is c naught, and n is equal to 1. For this case, there is an inverse relation between lambda and v, which means that shorter wavelength is associated with high frequency, longer wavelength is associated with low frequency. The wavelengths of importance in solar energy are basically the range between 0.29 to 2.5 micrometer. And as I said, it is not specifically or sharply given at these values, even to the extent that you may see these values might be different from one book or one reference to the other. So according to our reference here, these values are taken as a representation of the wavelength from 0.29 up to 2.5 micrometer. It includes the part of the ultraviolet, the whole visible range spectrum, and some of the infrared as well. Solar radiation outside the atmosphere is extending from 0.5, 0.25 to 3, which means that when it comes to the atmosphere, due to the attenuation of the rays, then the range of the wavelength shrinks slightly. One way to represent the energy associated with the radiation is through the photon radiation concept, where the E, the energy, is given by H, Planck constant, into the frequency. H is a constant. And from here we can say that, and the constant or Planck constant, the value is given here as 6.6256 into 10 to the power of minus 34 joules second. What is worth looking here is that the relation between E and frequency. Higher frequency means higher energy. Remember, frequency and the wavelength are adversely proportional, which means that higher energy is associated with short wavelength radiation. Lower energy is associated with long wavelength radiation. Probably it's worth now reminding you of something that is called the greenhouse effect. And the greenhouse effect, it's something which has had its own I mean, our concept or our inception, our receiving for the idea of greenhouse effect, that it is something which is negative, something that we don't like. But believe me, it has some sort of industrial applications where it can be made useful. And maybe during this chapter, I can talk briefly about at least one of them. So what is the greenhouse radiation or the greenhouse effect? It is basically that some surfaces are transparent to short wavelength radiation. This is the radiation or the strong radiation waves coming from a high temperature source. But they are opaque. They do not pass long wavelength radiation through. We are talking about global warming as a result of this. And actually, this is, it can be used in a way. For example, if you are driving your car and you decided to go to the gym or to the supermarket and you left your car in the sun, or maybe going for prayers, Jum'ah prayer, this is where you spend at least half an hour there. And then you have closed your car, you are leaving it in the sun. And then when you get back, get into it, what do you feel? Hot or cold?
Extremely hot.
Yeah, to the extent that sometimes if you have some plastics inside, you can find them melting or deforming because of the heat. This is why it's basically because of this greenhouse effect. Glass is transparent to short wavelength radiation, which means that the energy which is coming from a high temperature source like the sun can penetrate, can transmit through the glass. And they get into the inside of the car and they increase the temperature of everything there. The temperature in the car or the emission of radiation from the car it's a lower temperature source. And this is what we call long wavelength radiation. Glass is opaque. Glass does not transmit long wave radiation out, which means that there is continuously an energy in, but no energy out by radiation. And that's why it keeps on and on and on heating. And that's why sometimes they recommend if you are going to leave your car in the sun, then leave your window partially open. Why is that? At least to allow for convection currents to go in and out so that air from the outside or the hot air inside is going to move upward. If there's an opening in the glass, it will go out and be replaced by colder air from the surroundings. And then it helps alleviate this kind of heat somehow. Is there a way that we can make use of that? Yes, there is a way that you can make use of it. For one of the famous applications we used to use in water desalination is what we call the solar still. Solar still is a box. And in this box, basically what we have is a box which is made of insulating material, which is looking like this. This is all insulating material. This is insulating material, and this is insulating material, but the top here is basically glass. And we have seawater inside, or brackish water, any kind of water which is not clear, which is not clean. Seawater, I mean, by clean, I mean it has some contents of salt. That's why I said that inside here we may have seawater. What we do, we expose this to the sun. So solar radiation is going to pass through because it's coming from a short wavelength radiation, from high temperature radiation here. And as it comes here, the lower part or the lower surface here is painted black. So it's a black surface. It works like an absorber. It absorbs the energy and the surface itself gets heated. As it gets heated, it transfers the heat by convection to the water. The water will get heated. The water itself can absorb part of the radiation and get heated. So evaporation is going to start. You have some water vapor is going to rise up here. Water vapor is pure. This is salty water, but the vapor does not have any salt. So the water vapor is going to rise up until it falls into the glass. Glass is at a lower temperature. So what will happen to the water vapor here? Water vapor is leaving the surface. It will fall into a colder surface. So it will start
Condensate.
to what?
Good. Condense.
And the condensate, this is why we have a slope here. The condensate is going to roll on the glass by gravity. And then at the end here, you can collect it as sweet water. So one way for converting the seawater into sweet water for drinking is by using a solar still. We have several solar stills that some of your colleagues, students have made through their senior exam projects, and we have used and tested them. The basic idea is as simple as that. It's a passive unit. It does not need any machines. You don't need any power to run it except leave it in the sun. Definitely the performance is not excellent. I mean, you don't expect to get lots of water, of desalinated water or clear or fresh water from this. You can get something like 5 liters per day if you have a solar collector of 1 meter square. But anyway, it's one of the applications that are still useful in some countries that have issues or have problem with power. And what they do is that make units of this where the surface of the solar still can be made of wood or concrete or plexiglass, any insulating material. And the top you have a sheet of glass or maybe polyurethane. You can put it on the top and then you have your own system to create fresh water. So this is one of the applications where thermal radiation contributes a lot by just understanding the concept of greenhouse effect. Definitely, this is all tight. We don't allow air to come in at all so that the temperature remains higher than the surroundings. And then some improvements have been done into that, lots of improvements, like for example, using wax somewhere here below this absorber surface so that the wax melts during the day by receiving energy from the sun, and then after sunset the wax is going to start to melt. As it melts, it's transferring its latent heat of solidification to the water, so it keeps the water hot for about maybe 2 to 3 hours after sunset, and still the unit produces. So there are some ideas, all of them are related to the issue of receiving the energy and storing the energy and making use of the greenhouse effect in this case. So we're talking about the photon radiation, which is here associated or expressed in terms of the Planck constant and the frequency, which increases as the energy increases. And accordingly, higher frequency is corresponding to shorter wavelength, which characterize strong radiation coming from high temperature sources. And that would also mean that there is a minimum energy for the photon that is needed to make a change. And this specific idea is used in the PV panels. You have electrons that are sitting there. They need to be excited. So they receive the energy from the sun. And when they are excited, they leave their orbits to a higher orbit, or maybe they become free to move. And as they move, we take them to pass in wires or cables. And then this is how the electric energy is being conducted, or is being transferred and then generated in PV panels. You covered in your heat transfer course what is meant by a black body. A black body is something like an ideal case. Remember that we always need ideal cases whenever we are doing some sort of performance evaluation. You had that in thermodynamics, talking about the Rankine cycle and the highest efficiency, which is Carnot cycle efficiency, where you know that you can never get an engine which is operating at Carnot cycle efficiency, basically because of the irreversibilities. But anyway, this is not our topic today. But in heat transfer, you had also the issue of the effectiveness of a heat exchanger by comparing temperatures to the maximum possible temperature difference that you would know your heat exchangers cannot do unless its surface is infinite. But we needed that because we needed to see how good is our system. So we came up with the issue of the effectiveness as the temperature of the fluid inlet minus the temperature of the fluid outlet divided by the maximum temperature difference between the two inlets, hot and cold. And this maximum heat transfer is being used, although we know that it cannot be realized practically, but we are using it because we need to assess the performance of our current exchanger to see how good is it operating. The same thing applies for a black body. We assume that it is an ideal surface that absorbs all the energy falling into it. It does not emit any radiation. Anything falling into it does not reflect radiation, I'm sorry. All the radiation falling into it is going to increase its internal energy and raise its temperature. It will not transmit anything through it. It will not reflect anything to the surroundings. So it's an ideal concept, which is needed because based on that, we can look at our surfaces and say, is our surfaces depending on the application? Do you need an application where you need to absorb most of the energy or reflect or transmit? And then you can just see how much you are going to deviate from the black body. Black body is not only receiving all the radiation falling into it, which means that being a perfect receiver, perfect absorber, but it's also a perfect emitter, which means that the highest energy emitted from any source, from any body, any surface, is emitted from a black body. Do we find really black body in reality? Not really. We are a little bit lucky because if we are using a material which is called lamp black, this can be produced by incomplete combustion of heavy petroleum products, like tar, for example. Then this kind of material can absorb 99% of the energy falling into it. So we are almost here at a condition of a black body. So although it is an ideal condition, but we are very close to this ideal condition by having some materials that we use to cover the surfaces or to use as absorbers. Black body is not only a perfect absorber, I just mentioned a while ago that it's also a perfect emitter, which means that nobody can emit radiation higher than what a black body does. And we use this again for comparison between different surfaces, which is the same concept of talking about the Carnot cycle or the same concept based on the effectiveness of a heat exchanger or even heat and mass exchanger for chemical engineers that can be used for several applications. And there is a thought experiment which is being done here that a black body is and a non-black body or a real body, small in size, are both taken in a very big enclosure, and the enclosure is very well insulated. So it does not allow the energy to go through it to the outside. And there's a temperature difference between that enclosure and these two surfaces. Eventually, with time, the amount or the temperature is going to reach equilibrium between them because the heat is going to transfer from the high temperature side to the low temperature side, and this is going to continue until thermal equilibrium is reached. So the temperature of the two bodies, the black body and the non-black body, is going to reach the same value. The black body receives the highest amount of radiation. It keeps all the radiation in. The non-black body receives part of the radiation or absorbs part of the radiation and reflects part of it. But when you are saying that both of them are going to reach the same temperature and they are in equilibrium, it means that the amount of energy in is equal to the amount of energy out. If the black body is receiving lots of energy, then it should be losing lots of energy as well. So, and this is from the idea that, or for this idea that the maximum emittance is coming from a black body. It is receiving the maximum amount of radiation in, but it is emitting the maximum amount of radiation out. Planck law Planck came and he got a relation, or he developed a relation through which we can estimate how much is the energy of a black body is given per unit wavelength. And anything per unit wavelength, we call it monochromatic. So the equation that we have in front of us here is equation which is providing us with the monochromatic emissive power of a black body. And the monochromatic emissive power of a black body is given here as a function of Planck constant, speed of light, and the wavelength. K is what's called a Boltzmann constant, by the way. So this equation is providing us with the value of the emitted power or emissive power per wavelength. If you plot this, you can get the emissive power. You can plot it for isotherms, for example, lines of constant temperature. You say, for example, I'm going to assume what is the temperature coming from the surface of the sun, 5,777, or you can approximate it as 6,000. You substitute for a temperature of 6,000 here and change the values of lambda, then you can have a distribution of the monochromatic emissive power per lambda. Then you can repeat that for another temperature and another temperature and another temperature, and this is the figure that we shall be seeing in a while. The value of 2 pi hc0 square, for simplicity, because it's all constants, it can be given as C1, and the hc0 over k is given as C2, where C1 and C2 have these values that you have here in the bottom. So you have the monochromatic emissive power of a black body that is given as a function of basically lambda and temperature, the wavelength and temperature. The rest are constants. When we plot that, you're going to get this kind of relation at 6,000 degrees Kelvin, which is some sort of extraterrestrial radiation which is coming from the sun to the outside of the atmosphere. So this is basically what you can see, the line here. The line is going up here, up to a maximum value, and then going down. Repeat that for the temperature is 1,000, you get this line. Repeat it again for a temperature of 400 Kelvin, you get this line. So it seems that it starts from 0, reaches a maximum value, and then decreases again. Then came another scientist, his name is Wien. And what did Wien do? He said, I'm going to follow the locus of the maximum values. So this is a maximum value here. This is another maximum value here. This is another maximum value here. Actually, what did Wien do is that he plotted this for much more than only 3 values, but he did it for large number of temperatures and isotherms, and then he connected the locus of maximum value. Or he could have simply differentiated this equation with respect to lambda to see what's the value of maximum lambda, how much is the energy associated with maximum lambda. And what he found here is that the value of lambda maximum into temperature is equal to 2897.8 micrometer into Kelvin. This is referred to as the Wien's displacement law. It is saying that for a certain temperature, you can get lambda maximum based on this equation, or for a certain lambda, if it's maximum, you can get the course, or you can get the temperature at which this value is maximum. So this is one way that you can make use of the Wien displacement law. And the shape of the distribution is what you see here in this line. Another way to represent that is by, actually, when you look at the figure which is given here, the y-axis is a logarithmic scale. We're going from 10 to the power of 2, which is 100 to 100,000 to millions, and this is going in a log scale. But doing that in a normal scale by normalizing the value of E black body radiation to the E black body radiation maximum, you can get this figure. And what we need to look or to see from this figure is the range. The range of wavelength which is associated with very high temperature, it is this. the range of wavelength which is associated with lower temperature, the 1000, which is this, and then for the 400, which is this. And this again is another indication that higher temperature, which is basically high frequency or short wavelength radiation, is associated with a short wavelength. As the temperature goes down, then it will be associated with longer and longer wavelengths and so on. Stefan-Boltzmann equation came from integrating the monochromatic black body radiation over the entire range of the wavelength. Does thermal radiation go from 0 to infinity? The answer is no. It is only going from something like 0.1 up to 100 or maybe 1000. Why from 0 to infinity? This is for the mathematical simplicity. We said that radiation is from 0.01 to maybe 1000. What about below 0 to from 0 to 0.01? There's no radiation, there's no thermal radiation, which means that putting it will not hurt. The same thing if it's greater than 1000, there's no thermal radiation. But to make the integration easier, we're going to make it from 0 to infinity. And doing that, it will result in sigma T to the power of 4. Sigma is the Stefan-Boltzmann law constant, and T is absolute temperature raised to the power of 4. These equations and the value of sigma here is given slightly different from what you had earlier in heat transfer. In heat transfer course, we used to put it as 5.67 into 10 to the power of minus 8. Here we are given 4 digits for the constant rather than just 67. That 69 is given as 70 and then to the power of minus 8 for simplicity. But this is given here to be a little bit more detailed. Starting with Planck constant, we have the equation 361 here. And then values have been, we said when you integrate it, you get the total black body radiation as we did in the previous equation here, which is black body radiation over the entire wavelength range. What if we need it for a fraction of the range? Going, for example, from 0 to 0.1 or from 0 to 0.5 or from 0 to 0.7, like that. So in order to do that, this has been done by several investigators, and they came up with a tabulation of these values, doing that integration, as you can see it here, and getting the fraction of the energy compared to the black body radiation for the entire wavelength. Then comes the issue of the subtotal emissive power. You need an emissive power for a certain range of the wavelength, but here it is given with respect or a ratio of the total radiation over the entire wavelength range. Why is that? Because in order to make it easier to integrate this equation, here you have lambda and T. So if you are going to divide this equation by sigma T to the power of 4, then you are going to get that sigma or lambda into T to the power of 5. Here, lambda to the power of 5, and then you are going to divide the equation by sigma T to the power of 4, then this is what you are getting here. The temperature becomes temperature to the power of 5. Accordingly, when we do that, we are going to get the equation as a function of lambda T. So lambda T becomes as if it's a single variable that you are going to integrate your equation with. And doing that, the values of the integration are being tabulated here so that you can get fraction of the solar energy falling at a certain value of lambda T. So in order to estimate the fraction, you need to identify what is the wavelength and what is the temperature. You have seen this in radiation heat transfer courses before, and you used it, for example, some of the examples I remember in the radiation heat transfer chapter talk about how much is the fraction of the energy that coming from the sun, which is falling in the visible light. And the visible light is being given as lambda is going from 0.38 to 0.78 micrometer. And what you need to do is to consult this table to get this value. So this table is not exactly the same as the tables that we have in chapter 1 and chapter 2, because here the values are clustered in terms of lambda t. In these tables of chapters 1 and 2, basically it was only lambda versus the fraction. So that's the difference between this table and the other tables. The example that we have, I'll be showing it to you in a while, but many of the applications that you want with the use of computers is making it hard. If you need to estimate a certain amount of radiation by writing a program, you cannot stop the program and go and search for a table and a value in the table and then come back to the program and put it in. But you need this table to be put in a form of an equation so that you can just put the equation in your model and you can solve it without having to go back to the table. And that's what has been done here by Seigel and Howell. And Seigel and Howell were basically some of the pioneers of radiation heat transfer. And they came to represent that fraction F from 0 to T, the sub, or the ratio between the sub total emissive power and the black body radiation for the entire wavelength. This ratio F from 0 to lambda T has been given by that equation. And he said for this summation that we have here, it's enough to take the first 10 from N1 to N is equal to 1 to N is equal to 10. This is accurate enough. You don't need to go for more, you don't need more items or more parameters, more terms above N equal to 10. So from N equal 1 to 10 is good enough. You can put that in a loop in your computer program, and then you can calculate the values that are going to be here stored in a table. Let's have this example as, to close with. And the example is basically asking you to assume that the sun is a black body at 5,777 Kelvin. What is the wavelength where the maximum monochromatic emissive power occurs? And then what's the energy from this source that is in the visible part of the electromagnetic spectrum, which means that how much of this energy is going to be, this is exactly the same example that you had taken before in heat transfer course in radiation, in the visible range, which is between 0.38 to 0.78 micrometer. I was planning that we're going to go a little bit more in this class so that I have another example that I was going to ask you to solve by your hands as groups. So maybe we can do that early in our next class, inshallah. So the first thing here, we are going to go to the Wien's displacement law. And he's asking for this temperature, what is the wavelength which is corresponding to maximum radiation? And that's something which is easy to do because our temperature here is 5,777. So lambda maximum into 5,777 is equal to this quantity. So lambda maximum can be determined easily, which is 0.5 micrometer. So this is the first part of the example, as you can see here. The second part of the example is asking from the table that we have shown earlier, we need the fraction of the energy, which is within this range, within a range of lambda from 0.38 to 0.78. So what we are going to do, we are going to look at each one of these borders at the 0.38. This is lambda, but the table has lambda t. So we have to multiply the 0.38 by 5,777. You can get lambda t, and then you can get the corresponding value of that ratio. And then multiply the 0.78 by 5,777 and get the corresponding value of f from 0 to lambda. And then the difference between them is your fraction. Let's get back into the table and see here. I'm just using my calculator here. For the 0.38 multiplied by 5,777, the value is 2195. And the 2195 is basically here. We are somewhere closer to the 2200. So we're talking about 10%. So fraction of the radiation here is about 10%. Fraction of the black body radiation in the range from 0 to 0.38 is given here. and the 0.78 into 5,777, this gets us a value of 4,506. So we're going to go to the 405,000. We're getting something which is 0.5643. So 56% of radiation fraction to the black body is basically given at that wavelength, which is 0.78. So the range that we have is going to start with the 10%, 0.1, and it will end up with 0.56. So the range itself is covering the difference between them. The 0.5643 minus the 0.1, so it's almost 46%. We did this trial before. We did it in chapter 1. Go back to chapter 1 to example 131, and you'll find that the value have been calculated there to be 48%. And this comes right away from the figure we used in example 131. So get back to that example and compare the value with the value that we got here. You'll find that they are approximately close to each other. In heat transfer course also, you defined radiation intensity and radiation flux. The radiation intensity is defined as the amount of energy passing through an imaginary plane, which is per unit, imaginary plane per unit area, per unit time, per unit solid angle, whose central direction of the solid angle is perpendicular to the plane. So we have a source of energy, which is an emitter, for example, this one, and we assume that there is an imaginary surface, a hemisphere above it here, and the intensity here is amount of energy which is passing through a unit area, which is A1 here, per unit time, per unit solid angle, and this portion has been selected so that the angle which is coming here from the source to the center of this body, it has this surface is perpendicular or normal to that ray which is coming from there. Another thing which is important here is that the intensity is adversely proportional to the area. If the area is doubled, then the intensity gets to the half value. If the area is 3 times, then intensity goes to the third, and so on. When we'd like to find heat transfer between surfaces in a vacuum or a non-participating medium, assuming a non-participating medium, again, to remind you, this is the medium that does not absorb part of the radiation. Air as an example of that. Radiation of the sun passes through the air and the air does not get heated. And alhamdulillah, this is a bliss. If air is getting heated, you can imagine in summer we could not live, because the air is going to be heated by the sun and then we cannot breathe. We're going to, we can suffer then. So air is not heated, but carbon dioxide gets heated, absorbs the energy. And this is why we're talking about global warming, because the higher the carbon dioxide in the atmosphere, it absorbs radiation, then the higher the temperature of the atmosphere. So the whole temperature is of the earth, the surroundings is getting higher, and that's the global warming they are talking about. And that's why people are looking for reducing the value of carbon dioxide as much as possible. Probably you've just heard maybe last week, and maybe I can close by that for our class today, and then we'll pick it up from here next time, inshallah, that Elon Musk, the richest person in the world, he's the owner of Tesla cars company. He said that he has a prize of, I'm not sure whether it's 10 million or 100 million.
Doctor,
Yes.
I can't hear you properly.
You only or all of you?
I can hear you, Doctor.
We can hear you, Doctor. It's a local problem in your machine, maybe.
Okay. Abdullah Dosri, did you mention my name?
I have it here in front of me, Abdullah. I can see it. I did not take the attendance, but I'm seeing your names all here.
Okay, thank you.
Fine. So I'm just closing with this, that Elon Musk said that he's going to give a generous amount of money as a
100 million, Doctor.
somebody who's able to reduce or get a machine which is able to absorb carbon dioxide from the atmosphere in an effective manner. And he left it open to the whole world for somebody who would think of that. So why is this? It is because of that effect of carbon dioxide in increasing the temperature of the air around us. And this is an issue. With more carbon dioxide emissions, with more and more warming, and warming here is going to make not only the issue of suffering of the high temperature of the air, but it's going to result in melting of the ice caps and icebergs. The level of the water in the oceans is going to get higher. And some cities that are on the seashore would expect in 5 to 10, in 50 to 10 to 100 years to part of it is going to be covered by the water because of the high level of the oceans. And even some cities started to put some blocks so that they can protect the shores against this. So it's a serious issue. And that's why here the vision 2030 of the kingdom is mainly focusing on the utilization of solar energy as a main source of energy, instead of relying on the fossil fuel, which results in a considerable amount of carbon dioxide emitted to the atmosphere. So I'm going to stop here, and then we'll pick it up from next time. Next time, we're going to have like an exercise where you are going to join hands all together. And I would try as much as possible to make this exercise at least once a week, if not one every lecture, so that we can just get some sort of active participation from your side to the class. So thank you, and we'll see you next time, inshallah. Remember, homework number 2 is already available there on the blackboard. It is due a week from today, and homework number 1 has been adjusted and ordered in a proper manner. I'm talking about the solution of that. See you next time, inshallah.
See you. Thank you. Thank you, Doctor.
Thank you, Doctor.
Thank you.